Good morning, everybody. So we're gonna spend a quick couple minutes here talking about Windslab Avalanche problems. All right, I'm gonna talk about this from a little bit of a more high-level perspective. We're not going to talk about a lot of the basics here, and those are kind of topics that would be covered in your typical area course and things. So we might hit a little bit on it, but we're not trying to really introduce this problem from a basics level. So just quickly summarizing Windslab Avalanches, right? The main idea is that they're being created essentially by this idea of mechanical rounding, right? So as the wind is blowing the snow across the landscape, those snowflakes are being broken into smaller pieces, hitting each other, hitting the terrain, and as those smaller pieces come to rest, they're going to pack more densely, right? And so that mechanically rounded snow, less or more density, and that density change is really what's creating the slab of the avalanche problem, right? And so we're going to find them in areas where the wind collects the snow, right? So those lee zones, that can be ridge tops, that can be cross-loaded gullies, those can be like mid-slope rolls in some cases if you have like downslope wind, right? So a lot of different areas, and so that variety of distribution is something that needs to be sniffed out. Where is that problem really collecting? And then the other question we're going to be asking ourselves is how rounded has it become, or how hard has it been packed, right? And so to what extent has it been mechanically rounded into the denser slab, right? And so that variable hardness is really important, and that the variable distribution is really important, right? These avalanche problems as well, if they are true wind slabs, they do tend to take steeper slope angles to release. It's pretty unusual to see wind slab avalanches releasing in below like the high 30s, even into the 40s, right? And that's assuming this is indeed a true wind slab and not a wind packed slab sitting on another kind of like persistence, right? So true wind slabs definitely tend to take a little more. Uh, so what we can look at here is a video from Rocky Mountain National Park from an area course a while back. And so one thing we can look at here in the crown line, this avalanche, right, is this variable distribution, right? So this is really key. In this case, it's quite a small avalanche. I was able to break through the thickest part of the slab and initiate the avalanche. But imagine this kind of situation extrapolated to bigger terrain with a much deeper avalanche problem, where we have maybe a 2.5 foot deep wind deposit of firm dense snow in the start zone here, and then it tapers out into the sides of the deposition zone and the bottom of the deposition zone. So we have this big like lens of snow. It's very easy in these harder avalanches to have someone descend across the top of the start zone of the avalanche, the top of the avalanche slab, and not be able to trigger it, do that bridging effect of that thin to thick hard slab, right? And as they descend lower, where the slab tapers, they're able to initiate the whole avalanche and rip out the terrain above them as well, right? And so that variable distribution is with these harder wind slabs is really going to cause this avalanche problem to behave in some cases with that unpredictability associated more with the persistent avalanche problem, right?
Wow, it was bigger.
Right. So we can look at the same avalanche from a slightly different perspective now. Right. Notice the surface character of the avalanche. Right. It definitely is kind of this hard, punchy, unenjoyable ski surface. It's definitely on the harder side of the avalanche problem. Right. We notice the crown line as it initiates. It actually pulls out terrain like not only downhill of me, but also kind of traveling across and almost uphill. Another characteristic that's generally more associated, right, with that persistent slab avalanche. We're not usually seeing surface instabilities like ripping out above the person initiating them. Right, a couple different interfaces in there from different periods of transport. Little subtle different slabs kind of composing that main wind slab. Right, so a great example of that harder, more unpredictable, spookier kind of wind slab avalanche. This is another video of a softer avalanche character. Right, we can notice the surface character is like quite soft, enjoyable to ski in. Uh, this is sometimes referred to as like the snow has been creamed up a little by the wind, where it really hasn't become this like hard, dense slab. It's just like subtle density increase, right? But that's all it takes, right? So this is in some cases start to blend with what we might even call a storm slab problem. But this case being like right over a cornice, it's an obvious zone of deposition. I think the wind is really to blame here for that density change. The other thing we'll start to see is there's a high level of reactivity in this snow right along the cornice, right, where there's nothing reacting below the cornice. In this case, this really has a lot to do with what we refer to as the unsupported slope, So there's nothing below the slab right as it rolls over the cornice, and it makes it really easy for me to push it off the edge. Where if this slope didn't have the cornice there, I probably would not be able to get this level of reactivity, right? So in a lot of cases, that idea of an unsupported slope is definitely a trigger point where we see a lot of increase in instability. Uh, so that's where this is almost a way we can investigate steeper terrain using unsupported features, or in some cases even creating unsupported features with our skin tracks to kind of take that support away, create unsupported slope, and kind of increase the reactivity to see if maybe steeper terrain can produce that. Yeah, nice riding conditions. Here's another video. I believe this was from Rocky Mountain National Park again. I'm just gonna watch it this way. It looks like where we do have like another example of like kind of creamier surface conditions, right? The snow would be it'd be skiable. It'd be slightly denser snow, but still definitely soft enough to be enjoyable skiing. Good reactivity in this case. Once again, similarly unsupported. This in this case not because of a cornice, but because we've already initiated lower portions of the slab. In here too. Right. And so we can see there's another separate interface below here as well. Two like subtly different transport events. I think the bottom one was about 12 hours older, right? But still reactive. So we have two layers of reactivity, one being more reactive than the other, right? Once again, yeah, high level of reactivity in this case, there it's because in many ways we have removed all the support from the slope, right? Start to see that bottom layer react in this case then, right? Yeah, so wind slabs, really, really interesting avalanche problems. Right, key things to keep in mind is that assessing the how hard is the problem and what is the distribution of the problem going to be. This is the kind of avalanche problem that it is possible to interact with in a responsible fashion. But the key too is just making sure that you really begin to understand that problem before you move into consequential terrain, right?